Welcome to the sixth lecture on the topic sequence and series. And in this lecture, I'll discuss very important topic about the integral test and about the comparison test. So let's start.
Now we will see an important test that is called as integral test for checking the convergence and the divergence of uh, any series. So it says that suppose that fx is continuous positive and decreasing function in the interval k to infinity and that fn is equal to an, then if the value of this integral is convergent, then we say that the series is also convergent, and if the value of this is divergent, so the value of the series is also divergent. So let us prove this result. So we will to prove this, we will prove it for k is equal to 1. That is, we will prove the integral test for k is equal to 1, and the proof for journal n is similar. The proof for the journal n will be similar. So let us see the proof. That means that I am talking about this A, that we will consider that this f is continuous positive and decreasing for this interval, and we will prove this for particularly for k is equal to 1, and similarly the proof will follow for journal n. So let's start the proof. So now we will start the proof. Consider this figure, this I call figure 1, and now see that if with this I call this coordinate as 1a1, this as 2a2, this as 3a3, this as 4a4, and so on. So what will be the area for this? You can see that this is a1, so length into breadth you will have the area a1, and similarly you have area a2, a3, a4, and so on. So now from this figure I can see that if I take the integral from 1 to n plus 1 f of x, this is my f of x. So if I take the value of the integral, clearly this will be less than the sum of the rectangles. You can clearly see it, that the area under the curve is given by this area. So integration of f of x will give the area under this curve, and which is clearly less than the area of the rectangles. So I have this as my equation number 1. So this is very important to understand that how does this equation number 1 came. Now we will consider the another figure. Now we'll look at the second figure. This is my figure number 2. So again if I put the coordinate, this is my 1a1, this is 2a2, this is 3a3, and this is my n, so on. So this area will be a1, this will be a2. Obviously this is a unit area, and like length is a1 and breadth is 1, so this area will be a1, and this area will be a2, this will be a3, and this will be an. Now from this figure it is clear that if I say this as f of x, the area of f of x is greater than the area of the rectangles. So since we have considered like from our interval is from 1 to infinity, so I'll take the like my function is decreasing from 1 to infinite, so I'll take from 1, that is from 1 to infinite, f of x dx will be, sorry, for n 1 to n, this will be greater than a2 plus a3 till an. Now if I add a1 both the side, what I'll get a1 plus a2 plus a3 till an is less than, I have written it over here, and then a1 plus 1 n f of x dx, and now I call it as equation number 2. Now if we combine our previous equation, that is combining we get this. So it is very easy to see that if you combine both the equation number 1 and 2, you will get this inequality. So now if we take n tending to infinity in 3, so what will happen? You will basically get this. Now I'll call this as right left hand limit identity and this as right hand identity. Now from the right hand identity, if you consider this one, just look at this, and if you see now, if this is finite from right hand identity, if this integral is finite, obviously this series will also be finite. Therefore you can write that then, because it is smaller than this, so if this one is finite, then the smaller one will be also finite. So I can write then this is will be also finite, and so summation of an will be convergent. Now again from the left hand identity, now you consider this thing, this one. Now if you consider this and see that from left hand identity, if fx dx is not finite, then summation of an will also not finite, because if this quantity is not finite or going to infinity, then obviously the higher value will also go towards infinity and it will be not finite. So you can say that the nature of the series depends upon the value of this integral. Now if this integral is finite, obviously this will be finite, and if this is infinite, then your series will be infinite. And, remark regarding this integral test is that suppose the value of integral comes out to be a. Suppose this is your integral and this is a, that is finite, then you can say that a n, that is our series summation of a n, is convergent, but it is not the sum. That means that the sum of the series is not equal to a. Then you can write the, suppose the value of integral is a, then it is not necessary that sum of the series will be a. So there is no relation between the value of the integral and the sum of the series. So this is a remark which you need to understand, that it will just tell you about the value of the integral will just tell you about the convergence and divergent, and it has nothing to do with the sum of the series. So next we will take an example for solving how to show that the series is convergent or divergent using integral test. So here is the first example. Now I write use integral test to show convergence of the series this. So firstly I'll give it a notation that I'll call it as series this, where an represent the nth term of this series. So and then obviously f of n is equal to a of n, and I can write it as f of x is as 1 by x. For x it is defined for x greater than or equal to 1. Now observe that first that f is positive for every x that is greater than or equal to 1, and secondly f is continuous, and thirdly f dash x is equal to minus 1 by x square. This ultimately indicates that f is decreasing for every x greater than equal to 1. Now you can easily see that all the conditions of the Cauchy integral test are satisfied. So we can find the convergence or divergence of this series using the Cauchy integral test, since all the pre-requirements are satisfied, that f is positive, f is continuous for every x greater than or equal to 1, and f is decreasing. So we will consider, I'll write the value of integral as 1 to infinity. Since it satisfies all the condition, I can find out the value of this integral, and if it comes out to be finite, then it will be convergent, else the series will be divergent. So easily I can find its integral, that is, this is coming to be infinite. So therefore by integral test, summation is divergent. It is clear that since the value of the integral is coming to be infinite, therefore our series is also divergent. Now we will look on the another example. Now you want to check the convergence or divergence of this. So now here an is obviously your an is which is equal to f of n, and you can write in the form of f of x, and then see that clearly you can see that first f is positive, second f is continuous, and thirdly f dash x is less than 0 for every, you can say, for every n greater than or equal to 1. So all the conditions of the Cauchy integral test are again satisfied. All conditions so therefore again we can use the Cauchy integral test to tell the convergence or divergence of this series. So I would consider I consider I as a value of the integral, that is from 1 to infinity e to the power. Now if you solve this integral by putting e to the power x is equal to t, and if you solve, you will get this. So again this is what this is coming out to be, finite value. So what will you suggest about our series? That it is also convergent because your value of integral I is coming out to be finite. Therefore our original series, which was this, is convergent by Cauchy integral test. I hope this is clear. Now I will discuss an important result. So this is a result. So a series that you have a series, suppose that this is equal to and so on, where p is a real number. You can write as a real constant, and this series converges if p, where p is a real constant, converges if p is greater than 1 and diverges if p is less than or equal to 1. So we want to show this result. So let us see that first case 1, when p is greater than 1. So this implies that what will be our an? This will be 1 where for n greater than or equal to 1 and p is also greater than 1. So now I'll define f of x, which is equal to a of n. This is x of p. Similarly, x will be greater than or equal to 1. Now, first you can see that fx is positive, continuous, and decreasing. You can easily check it. So therefore, all the conditions of integral test are satisfied. So you can apply the integral test for this to check whether the series is convergent or divergent. So now I'll apply the integral test. Therefore, define I, which is equal to this for p greater than, here we are discussing for p greater than 1. So I'll have the integral as this. So this will be equal to which will be equal to 1 by p minus 1, which is finite. So for p greater than 1, you can see that clearly that the value of this integral came out to be this, which is finite, and therefore you can write, therefore by integral test the series this converges for p greater than 1. Now case 2, if I discuss case 2, which is for p is equal to 1. So what will be our series? This will be equal to 1 plus 1 by 2 plus 1 by 3 and so on. And I have already shown in an example that this series is divergent by integral test. It was my first example. So you have proved it already that this is a divergent series. Now we are left with our p less than 1. Case 3, when p is less than 1 but it should be greater than 0. So then we have again all the conditions are satisfied to apply the integral test as we have shown in case 1. So I'll consider it as I1. So this will be the value of integral will be this, which will be equal to this is equal to so you can easily see that this will go to infinity as the value of p is less than 1. So therefore again by integral test, since the value of the integral is coming out to be infinite, therefore by integral test summation of 1 by np where p is less than 1 is divergent. So we have shown an important result using the integral test, that this series will be convergent if P is greater than 1, and it will be divergent if P is less than or equal to 1. Let us do a last example on the integral test. So we want to check the convergence or divergence of this series by integral test. So here it is easily seen that I'll write summation of an is equal to this. So where an is, which is equal to f of n for n greater than or equal to 1. So for f of x, that is equal to ln x by x, x is greater than 1, we clearly see that all the pre-requirements of integral test are satisfied. That is, f is positive for every x greater than or equal to 1. Secondly, f is continuous for every x greater than or equal to, and thirdly, f dash x is, you need to find out this f dash x. So I'll take the next page. This is, you don't know that what is your f dash x. So let's find f dash x, which is equal to, now if you want this to see when this function is decreasing, put this as less than 0. So this will give you 1 minus ln x. You are trying to see for which x the function is decreasing. So ln of x is greater than 1. This implies that x should be greater than exponential, that is 2.71828, for the function to be decreasing. Therefore the function fx is decreasing for x greater than e, or greater than or equal to, I can write it as 3. So now all the conditions for the integral test are satisfied, so we can apply the integral test. So I'll write as I, which is equal to 3 to, now it is very important to see that the Cauchy integral test, the conditions for Cauchy integral test are satisfied for this x greater than or equal to 3. So I'll apply for this value interval only, for which the condition, the prerequisites of integral test are satisfied. So this, putting ln x is equal to t, 1 by x dx is equal to dt. So I'll solve this integral, and this came out to be ln 2 this. You can easily see that this is infinite, and that means that this is not finite. So by integral test, our series, that is the main series, therefore by integral test our series this is divergent because the value of the integral is coming out to be infinite. So the integral test says that if the value of the integral is not finite, then the series will be also divergent. Now we will see another important test for checking the convergence and divergence of the series, that is called as direct comparison test. So it says that suppose that we have two series an and bn with an and bn greater than or equal to 0, then for all like it holds for all n, and this inequality also holds for all n. Then if bn is convergent, then an is also convergent. That means that if this larger one is converging, then this smaller one is also convergent. And the second one says that if an is divergent, then bn is also divergent. That means that if this smaller one is diverging, then this bigger one will also diverge. So I think that the statement of this test is clear. So now we will take one example which uses this test to check the convergence or divergence of a series. So suppose that I want to check the convergence and divergence of this series. So clearly I can write summation of 1 by n factorial is equal to, and now this one will be less than, these two terms are equal but other terms will be clearly that this the series I am writing is greater than the original series. So this will be equal to summation n from 1 to infinity 1 to n minus 1. Now you can easily see that this is convergent geometric series. So what you can say about this, the original series, since this is convergent geometric series, as this has r 1 by 2 which is less than 1, then obviously this one is convergent geometric series. Then by direct comparison test we can say that the original series is also convergent, and therefore we will write, therefore by direct comparison test this summation 1 by n factorial is also convergent. I hope this is clear. So if I write down a question that you have a series and you want to check the nature of the series, that whether it is convergent or divergent. So now you can easily see that I can write the nth term of this series, it is less than, now the task that is remaining is that we want to know the nature of this series. Now how can you find out the nature of this series? So you have already studied about the integral test. So if you notice that if I write f of x, this is e minus x. So if you notice that this is continuous, positive and decreasing function. So we can use the integral test for checking the convergence and divergence for this series. So let's use the integral test. So if I use the integral, this will be equal to limit t tending to infinity. This will be, and you will find it that this is coming to be finite, that is its value is 1 by e. So since converges, this implies that our original series also converges by direct comparison test. Now let's have a look on few more examples. So now you have a series, this, and you want to test the convergence and divergence of this series. So observe that this inequality will hold, and which is equal to 1 by n. Now since you already know that since n from 1 to infinity 1 by n diverges by you already know by integral test you have shown that this series diverges. Therefore, what about the original series? By direct comparison test, the original series also diverge, that is this. Because you have already seen that if this is divergent, that is you can see that this lesser, if some lesser quantity is divergent, then this one will also diverge. So this is the direct comparison test.
Of the important topics from the sequences are covered. Now I request you to go through the book Calculus and Analytic Geometry by Thomas and Finney, ninth editions or even the higher edition, and practice more and more problems on sequences. Thank you.